Welcome to our weekly Next Chapter meeting. We have our guest speaker, William Yan from Duke University, and he's going to be talking to us about macrophage activation and traumatic brain injury. So thank you so much, William.
Thank you, Ms. Poole. Hi, everyone. My name is William, and I'm a senior at Duke studying biology. Today, we're looking at macrophage activation and traumatic brain injury. So, first of all, what are macrophages? They are a type of immune cell in our body that basically builds a first line of defense against infections and heal the damaged tissues. So what they normally do is they eat harmful substances like pathogens, debris, or toxins, and help clean up areas of injuries or infections. And they also release these chemicals called chemokines or cytokines that regulate inflammation, and they can both be promoting the inflammation or anti-inflammatory. And we can see on the right, that's a image of the macrophage eating pathogens in real time, and then here's like a little cartoon of the macrophage eating the virus. Okay, next, how does macrophage play a role in traumatic brain injury? It is actually very prevalent that almost all of the TBIs trigger some activation. This kind of makes sense because this is kind of saying that after injuries, your immune system gets activated, and hopefully and most likely that everyone goes through this after some type of injury. And uh, this is a very normal immune response, and because it's trying to contain pathogens and clear debris. But long chronic inflammation is harmful because sometimes the macrophage also leads to secondary injuries by attacking our own neurons. And another thing that's important is called a cytokine storm, which is an uncontrolled release of inflammatory signals. And that causes widespread inflammation, causing tissue damages. And I kind of want to connect this to how flus and vi deadly viruses like COVID works. In a lot of the cases, it is actually not the virus directly killing the host, but rather the virus triggers a super panic attack from immune cells. They just stress out and release a lot of cytokines, and that turns out overstimulates the immune system, and the immune system starts clogging up, attacking our own cells, which leads to the final fatalities in the host. So that is the cytokine storm is just basically immune cells getting super stressed that it starts to attack our own cells, and that's that's not wanted in terms of any injuries. So looking at the timeline, when the immediate response after a TBI is that the microglia, which is the macrophages living in the brain, so local macrophage, we give it a name called microglia, they would sense the injury and then become activated quickly. And then the peripheral macrophages in the blood start to infiltrate into the brain through this disrupted brain-blood barrier. They would release cytokines such as IL-1 beta, TNF alpha, IL-6. All of these are pro-inflammatory cytokines to start the inflammation process. And the purpose of that is to clear the debris, contain the injuries, and then signal other immune cells that, hey, there's a injury going on that we should get activated and clean it up as soon as possible. So after 1 to 3 days, we would move into this early phase that the macrophage will shift into mixed phenotypes. So there are two distinct phenotypes of macrophages. One is called M1, which is pro-inflammatory. They produce cytokines, reactive oxygen species, and then can cause secondary damage, which is the unwanted part. But the initial part is great because it's trying to clear out the debris. The second type of macrophage is called M2, which is anti-inflammatory. So they would promote the repair and debris clearance. Uh, and this is generally wanted in the long term because the M2 are really toning down the secondary damage, the secondary inflammation, and trying to initiate the reparation process. Um, So there are a couple of blood markers to see these changes. So they have an early rise in ferritin, which is and then CD163, and these are inflammatory markers. That if we see the increase of these, which means that there's a more balance towards the M1 pro-inflammatory response. So then during 3 to 7 days, that's where the immune cells reach their peak activation. They have strong inflammatory response in the injured areas. And then there's also hemophagocytic activities in extreme inflammations. What this means is that the immune cell gets so activated, it starts to eats blood cells, and that will risk the danger of having not enough blood cells circulating in our system. And that also runs a high risk of cytokine storm, which I mentioned earlier was a really serious secondary damage to our body. Moving on into the long terms to week and month, that we step into the chronic phase where the macrophages and the microglia goes into a gradual resolution and shifts towards repair and scar formation process. So in this phase, the inflammation is generally not wanted because chronic level of inflammations will end up hurting our own cells. But regardless of that, some low-level inflammation will persist and then still contribute to any cognitive or motor deficits. Okay, so another similar symptom or a more general syndrome is called macrophage activation syndrome. It is a rare but serious immune system due to the overreaction of macrophages. So that often happens in the childhood with inflammatory diseases such as systematic onset juvenile idiopathic arthritis. This basically means that after arthritis, the macrophage gets very activated, and that leads to fever and many negative impact in our body. Another example is the systematic lupus erythematosus, which is a autoimmune disease that affect multiple organs. And then there's also inflammation in the blood vessels in children that's harmful for our system. And all of these can be classified as macrophage activation syndromes. So just a brief overview of the timeline for that. From day 0 to 1, often a viral infection will kickstart the process. Um, the macrophages are abnormally activated. Cytokines, like these activating cytokines, will be released, which leads to a cytokine storm, and that leads to a fever. And then from days 1 to 3, that's more early hyperinflammatory phase. The macrophage becomes super activated and then starts engulfing blood cells. This leads to a drop in blood, both red blood cells, which carries the oxygen, and the white blood cells, which does the immune response. Um, in addition, they also deplete platelets, which helps us with blood clotting. And with day 5 to 7, that leads to hyperinflammation, where the macrophages reaches maximum activity and there's widespread tissue infiltrations. And these macrophages, these immune cells, actually goes into multiple organs and starts eating up these organs. So how do we diagnose a super activated macrophage? There are different blood tests to do that. So if there's a ferritin that's over 684 nanograms per ml, that means the protein that stores iron away are storing irons away from pathogen um, is very elevated, which means that there's a lot of pathogens in our system, and that marks inflammation. Uh, and another check is checking for pancyto pancytopenia, which means that this basically just means a lack of blood cells because after macrophages gets really activated, it starts eating blood. When the hemoglobin is less than 90 grams per liter, or there's a low amount of platelets and neutrophils, that means these macrophages are overactivated to a degree that we don't want that. And last but not least is to check for overactivated blood clottings with uh, fibri fibrinogen smaller or equal to 1.5 grams per liter, because that's also when the blood clotting system gets disrupted when the macrophage starts attacking your own cells, and that's also indicated for that. Okay, so moving on, what are some treatments for this chronic activation of macrophages? One of the traditional way is using steroids. They broadly suppress inflammation by interacting with uh, intracellular receptors. There's other drugs such as cyclosporin, which uh, quiets the overactivated T cells. This is another type of immune cells that uh, cooperate with macrophages to cause damages to our own cells. And another drug is called anakinra, which blocks a key inflammatory signal called IL-1. Okay, so here is the important question is we know that TBI leads to some activated macrophages or chronic macrophage activation, but is it to a point where we can classify those as macrophage activation syndrome? And the general consensus, I've read through 3 to 4 articles, and the general consensus is that there's no evidence of TBI as a direct trigger of MAS. I've read a couple of case studies that shows that there are people with TBI that actually develops into MAS, but a causation effect is not being documented. But regardless of that, there's a couple of similarities and differences I want to discuss. The elevated macrophage markers, such as ferritin and CD163, is both elevated in terms of macrophage activation TBI and macrophage activation syndromes. There's strong cytokine releases, and there's a potential for systematic inflammation in severe TBI. However, MAS is normally systematic with multiple organs involved, and TBI activation is mainly localized in the brain. And for clinical MAS, there's fever, cytopenias, many other syndromes that really rarely across from TBI alone. So the general consensus is TBI leads to macrophage activation or even chronic macrophage activation in some cases, but not severe enough for MAS. So with that, I would like to thank everyone for being here and listening to this presentation.
Yes, that was great. And if anybody listening to this, if you want to learn more about it, because we've asked our Duke students to, keep the language technical because we want to learn about our brains and what's going on, but you can always stop the video and look something up. But thank you so much, William. We appreciate it.
Thank you.